is what can be done to get rid of such issues. And there are a lot of, or there are some, let's say, dynamic beam solutions. This is the most, let's say, prominent, that you move the beam. That was the first thing that was called beam shaping, and the brand name was wobbling. So in this case, you have a beam which moves through this melt pool, and the keyhole follows the beam. You can also shape the beam. You can make different shapes. Instead of round, you can, for example, make a triangle, or you can switch the shape even. So you make a triangle in this direction, then you make a triangle in the other direction, which gives, and again, a different effect on the weld itself. And the fourth possibility is that you can even mix the shapes. So if you switch the shapes very fast, then you get an average response of the melt pool, so what is going on. And the question is, what makes really the difference between these four basic approaches for beam shaping? And this is what I would like to address today. And it can be, from my point of view, it can be reduced to the question, when is a shape a shape? And I want to, you see, I have three names here in blue. We had many discussions, in particular with Jonas, who is today with us, so he can also give answer, and with Alexander, and Benayau from Civan, who has left, unfortunately. We had really many discussions to try to understand what this laser is making, how it is working, and how it is acting on the process. And today I want to give you really a basic overview over how the laser works. So I want to share a little bit what came out of these discussions. If it is boring, you can leave. And if you know everything already also, but if you have questions in between, I really ask you to ask these questions, just interrupt. It makes sense instead of just going through and fill you up with sometimes quite dry matter, that you also are allowed to ask questions. So let's start with the points. At the FSW, we had this DBL6 14 kilowatt laser, 32 fundamental mode beams with these parameters here. And these 32 beams are coherently combined, in the most simple case, to a plane phase front. So the overall phase front over these 32 fibers is plane. And if you now focus this on a surface, so you go to the far field of the laser beam, you end up with a diffraction pattern which has a strong point in the center. That's maybe why it's called point. If you go to the Civan software, which is nice to show what happens exactly, this is what is done. You set this point, you click in the center here of the drawing grid, and what you see then is here in the blue, I called it active area. In the blue active area, you get this diffraction pattern, which is unique for each position of this point. So this is an intensity as a function of x and y. And this is one of the first important remarks. If you start doing designing of processes, you cannot just look at this point. You have to look at the complete active area. And the active area is enough. This was designed that more than 99.99% of the complete laser, or total laser power, are within this area. So this is what happens if you set the point. Only for later on, this is the coordinate system, how it is used. X is in this direction. Here is the maximum set point you can set. Y is in this direction. Here is the maximum set point in Y direction. And in the active area, you get this Y active maximum here, and in this X active maximum in this direction. And this colors, this false color picture here is normalized to the maximum value, which occurs in the rectangular area here. So if you look at the 3D picture, you see the diffraction pattern with the side lobes, and you see the maximum, which is normalized to 1. It can be a little bit better explained if you look just in one direction. So this is along the X or the Y direction divided by the active area. That is normalized to this dimension. That's why it's 0.5 here and 0.5 here. Here it's 1. That's the normalized intensity. And what you get now is you get a strong main lobe here in the center of the area. This main lobe has a diameter which can be roughly calculated by the simple focusing formula, which you can find in the literature. There are some formulas which I will show. There is no need that you look today in details these formula. You will get the talk, I guess, Samuel. I hope so, that all the people get the talk. So if you then want to calculate yourself things, you will find the formula on my slides. And because the m square is given and the diameter of the array is given, you can make a very, very simple formula that the diameter of the main lobe is just some proportion is proportional to the focusing lens length. What is important to know that the main lobe contains about 60% of the total laser power. And then with the two values here, with the diameter and this number here, you get the simple approach formula for the maximum intensity. This is very simple formula. It's almost just the laser power divided by the square of the main lobe. So I just put all the numbers in, then you end up with this simple expression. What you can see is that this maximum intensity is only given by the laser power, and because the diameter of the lobe is only by the lens, so the maximum intensity is only given by the laser power and the focal length of your lens. So if you have chosen this couple of two values, of these two values here, you can no longer change the max or really change the maximum intensity, because changing, that was too fast, sorry, changing the laser power is usually quite slow. So you set it up and then you end up with a certain maximum intensity in the center. The side lobes, there are a lot of side lobes. Two are quite high, some are smaller. All these side lobes inside the active area contain, of course, the rest, 40% of the laser power. Which means, now first this one. So you have at the highest here on the side, which you can see also in the blue area usually, is about 6% of the maximum intensity in this point. This means that, that was too fast. This means that you have to consider the heating of the surface, the complete process really, including all the power which is put in the side lobes. And without giving a formula, if you look at the deep penetration threshold in welding, in keyhole welding of steel or whatever, then it might be that even the side lobes are above the deep penetration threshold, which has a completely different effect as if the two side lobes were below. So the message behind this picture here is, of course, the center point is important, and the intensity is quite high in the center point because it has the properties of a fundamental mode beam. But you have a lot of power also in the surrounding of the beam, and there is at least two side lobes here in the two-dimensional view, which are almost 10% of the maximum here. The next you can do, you can set the point at an arbitrary position. This is done by tilting the phase front. The phase front is tilted and then the beam moves to the side. And we're not sure why is this solved like this. The answer is very simple. If you would like to make a diffraction pattern here in the far field, which consists only of the 6 beams, so we start to form the phase front here, to get your diffraction pattern, the spatial resolution is very low. It's only 6 times 6 pixels. If you tilt the phase front, the resolution for positioning a beam is much, much higher because this angle can be adjusted with much smaller increments. Which means if you have a coherently combined laser, like this is, It must not be a Civan, by the way. Any conveniently combined laser that has this problem. You have only a few fibers, so if you want to have high resolution, you need to go to the moving point. So for me, this was at least an important finding to get the idea why did they solve it, and I found it's quite clever from Eyal and Bayanayao really to find this solution. Okay, you can move now this bond to the right instead of here it's here. Then what happens is, what you can see is that the main lobe here is getting a little bit weaker, and the highest side lobe here on the left side is getting higher, and the side lobe on the right side even disappears out of the active area. So what happens if you put your point just a little bit aside? Everything starts moving, in this case, to the right. That's what you have seen. If you go to the maximum point here, to the maximum set point, you end up with two identical lobes. So the side lobe to the left is now the same side as the same height as the main lobe, which was in the beginning in the center. And by the way, this is really the definition of XZ max. The maximum setting point was defined to be there where the two lobes have the same height. And due to this symmetry, you get the identical result if you go to the left. So if you put instead of putting your set point here, you put your set point here, then you get the identical picture. So it doesn't matter if you click once here or click once here, you end up with the same result. And the behavior can also be described quite simply. You see that the lobes here, they follow an envelope, this orange dashed curve that you can see here. So moving to the right, this lobe increases, this is decreasing, and then here at this point we have the two at the same height. So the height of these two intensities, of the maximum intensity, follows the slope. And again, you can start calculating a little bit if you want. So you can see that the envelope can again be calculated if you know some of the laser properties, and you end up with a simple formula here. As I told you, if you want to know it, you can go into detail. What you get is the maximum set position where you have the same peak height, and what you get is the maximum of the active area, which contains 99.99% of the power. So you have all these definitions, which are quite clear, and what is nice, it is only defined by the focal length of the focusing lens. So if you want to change everything in your blue area, or in the green, no, let's say in the blue area, in your active area, the only thing you need to do is to replace your focusing lens, and then you get different properties. And for your no, let's just before say this, you can also put it, of course, anywhere in the green drawing area. Then you get usually 4 points. So this is what the highest point to the left, the highest at the bottom. There is one in the corner. It has a rectangular shape because the arrangement of the fibers is also or square about. So you got these 4 points, and the maximum can then be calculated with a 3D envelope. And for your convenience, I have summarized it in a table here. So if you have a focusing lens of this focal length, then you have defined values for the maximum set point in x direction, for the maximum x point of the active area. You have the diameter of the active area, which is twice this, of course. You have the diameter of the main lobe. This also might be an interesting value for you. And for a certain laser power, in this case for 12 kilowatts, which we had at the IFSW, you get the maximum intensity which you can achieve in the center of your active area. So the only thing you can do when you want to change this is you must change the power or you must change the lens. So this is the very, very basics. That's how the laser works in principle. You put a point somewhere, and you can move it around in your grid, and for every position you get a defined value for the maximum intensity, and you get defined values for the highest side lobes. So this was the first step. The second step is you can move the point, whatever moving exactly means. It's not really moving, it is repositioning. So what you can do is you can put your point somewhere, then you can erase this, you can put it in the next. Let's go back again and show it again. So then you just put it at a new position, and what you can see is that your pattern is moving together with the set point and is moving back. So this capability or this repositioning gives a kind of moving of this point. It's discrete values, so it's not really continuous, but because the resolution is quite high, as I already mentioned in the beginning, you can quite nicely reposition this point. And here I have to introduce a number which I call dwell time. So this is the time how long a point stays at a certain position. I numbered them, so it's each position, how long the point is there. So you will see later, depending on how the configuration is, it's a difference if a point is a long time at this position or it's just a short time. So this is dwell time. This is an expression which I will use in the following. And of course, this moving can be done very fast because the minimum dwell time of such a point is 12.5 nanoseconds. This is given by the 80 megahertz, which is the maximum modulation frequency of the electro-optical phase control of the laser. So because this can be done really with 80 megahertz, the shortest duration where you can set up a point and then switch it off again is 12.5 nanoseconds, which at least to my opinion is a quite short time. And, oh, it doesn't really move nicely. Let's go back again. Maybe it, so it looks like the transmission is a little bit low in Teams. So this would move just forward back. And because Jonas has made this nice calculation together with Alexander, I just like to show it in 3D. It looks nice. It really looks like the beam is moving from one side to the other, but you should always keep in mind, you just have positions. This is one of the secrets of the laser, you have positions, but you can reposition very fast. I hope everything is clear up to now. Maybe it's too boring, just tell me. But that's how it works. The next is you can do shapes. That's what Civan is calling shapes. And of course, again, you have single points. That's what I wanted to point out in this first part. You do not have shapes. If you want to have shapes, you need to shape your complete face front. You can only tilt it. That means you get always just these points. And if you want to have a thing called shape, then you need to make a sequence of points. And this is, of course, a sequence of diffraction patterns. So I put my first point here in the corner, that's I equals to 1. If I put it here in the corner, I have the 4 points which have the identical height. Then I can set the next point, I equals 2. Then I got these 2 points. So I got not just 1 point here, I really, for every set point I do, I get a complete diffraction pattern. And now I can really go through 9 points here. Oh, it's a little bit, it's not that continuous. And then I end up, so the 9 would have been here, 1 is here, 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 and so on. And then going back, and the last is I equals to 9. So this is the last point down in the corner, and you can see I have the same shape as in the beginning, exactly the same diffraction pattern. Let's call it diffraction pattern. I have the same diffraction pattern as I had in the beginning. And a shape now consists of a number of positions where you put your points. Now it's getting hard, sorry. So you have number of positions where you click your points. In this case, we had 9 set positions, and each of these points, in this case 9 points, creates a diffraction pattern intensity of the eth point from x, y. So it covers the whole active area all the times for every point I set. And now, if I start doing this, I let somebody in, huh? If I start doing this, then the fluence distribution is sensible, is interesting. So instead of looking at the watts per square centimeter, it's interesting to look at the joules per square centimeter, because now the energies start summing up that you deposit. So what I end up with a fluence distribution in the active area, which is given by the intensity distribution times the dwell time at this position. And this is true for all of my 9 points. Ami, you probably have to admit somebody to enter the
I am
meeting.
trying, having some technical problems there.
Sorry. So is this clear? And of course, here's just a list in the shape generator software. And during processes, during laser processing, they have the same sequence as you have defined it here. This is just a remark for the Civan stuff. What you can do now, you can click one point more than once. For example, the one in the center. This means that the pattern looks a little bit different now. These are a little bit less bright, and this is the brightest one. You can see I have clicked twice here at I equals to 5. You have twice this at the coordinate 0, 0. And this means that I have 2 clicks at this position. And this means that I increase the dwell time at this position by this factor here. I will give you an example then what this means. It makes it a little bit complicated, but that's how it is. So if you click here twice, your number of clicks at this point is doubled in this case. So what you can do now, if you increase the dwell time, you can increase the energy which is deposited in the diffraction pattern for the point at this position. So this is exactly what you do, because the time for each point remains or is the same then. So if you click twice on one point, this means that you increase the energy or the fluence, which is deposited here in this case, is doubled compared to the other points, let's say it this way. And what is important to know, which was one of the difficult things to understand, you only increase the fluence, you do not increase the intensity. Because the intensity is only given by each of the diffraction patterns. So you have your intensity distribution in the diffraction pattern, but the energy distribution or the fluence distribution results then from the number of clicks. It might be difficult to follow, but please try to understand what I'm saying with it. Okay, and then what is important, which relates then to the software of Civan, the total number of clicks in a shape, not the total number of points you can see. The total number of clicks in a shape is the total number of points. That's what's called in the Civan software, number of points is the number of clicks. So this means in this case, we have the 9 positions, as said in the beginning, but in the Civan software, you will encounter the number np tot is 10. In this case, you have 10 points, also if you only have 9 points. Is it clear? So clicking here twice makes that your np is increased, but the number of positions is still the same. And if you now do this very fast, you end up what is called shape. And for the shape, in this case, you see I have only one click in the center now. So we have 9 set points and we also have 9 click points. It's the same, so this is 9 points. Every has almost the same brightness, not identically due to the diffraction patterns, but it's almost the same. Here in the center, we only have one click now. And now the shape in the active area represents the sum of this deposited energy by the patterns. So this formula must be shown. So you have this fluence distribution for a single click, and then this fluence distribution for the shape is just summed up. So what you end up with, if you have such a pattern, you end up with a integrated, or because it's discrete, it's only a sum. You have the sum of all fluence distributions of each click you have made during generation of your shape. So this is, in fact, might be a shape. And of course, there is only one limit again, but I do not want to discuss this today. If you move very, very fast over the surface with your shape, then this means that sorry, my mouse is here. So if the movement over the surface is more than, let's say, half of the diameter of such a fundamental mode lobe, a little bit, maybe 1/10 or so, that can be fine. Then this does no longer fit, because then you have also translation during generation of your shape. So for today, I want to stick to, let's say, to slow movements where this formula is correct. Otherwise, you need to reconsider everything. And what means fast? And fast will be addressed soon. And the third thing that you can do now with Civan software is you can make sequences of shapes. Sequences of shapes is simple. You can make hourglass and spiral, don't know what the name of this is, and the smiley, of course. So this might be a sequence. It can be 24 or so, I don't know, I don't remember shapes. Or what also can be, it can always be the same. No need to change. The definition, as I will show later, doesn't distinguish between these two cases. So a sequence of shapes just mean you make a shape, you make a shape, you make a shape, you make a shape. So this is sequence of shapes. That's simple. And please don't forget, with my finger here, each of these shapes is a sequence of points. So what you have, if you have a sequence of shapes, you have sequences of points here, sequences of points here, sequences of points here. So you always keep in mind this picture, please. You always have the beam moving around very, very fast in the active area, then it makes another movement, then it makes a third movement, and so on. That's what in principle happens with this laser. Are there any questions up to this point? It makes sense to have 10 seconds of interruption to press once, because now it's getting a little bit complicated. But now I guess is the more interesting part for today. So let's come to the shape generator. Here you can define now really numbers, time constants, frequencies. Up to now it was just the basic principle how it works. You have your moving beam, you make your shapes. And now, from my point of view, it's getting to the point which is really important to understand to solve issues during laser processing. So we have this window, that's the shape generator. No, that's the shape tab in the software where you get this window. And in the first case, I stick to my simple example of the 9 points here, each clicked only once, that makes it simple. So this is the ID, how it's called, and the number of points, of course, is just given how you design the shape. So, but it's you who define it. So it's a user-defined value. You make the shape, you click every point once, you end up with NP tot, number of clicks is 9. So this is clear. That's what I've explained now. So, and now the second point is, you have to define frequency, it says. So it means shape reference frequency. This means how long or how fast, how often per second you make all the 9 points in the shape. So how often you move, I don't see my mouse, here it is. So how often you make this whole movement here per second. And for the example I'm using here, it's 500 kilohertz. So you make these 9 points 500,000 times per second in the row how it was defined in the shape definition. So this is the shape refresh frequency. And for convenience, sometimes it's nice to have frequency and duration. Sometimes it's much nicer to either speak of frequencies or speak of times. Both are fine for me, but for convenience, I have defined both. So you have here the frequency, 500 kilohertz. I would like to define also the shape refresh time. So this is the shape refresh frequency. This is the shape refresh time. Very simple. It's just 1 over the frequency. And in this example, the shape refresh time is 2 microseconds. Sometimes it's nice just to see the number. For me, microseconds are easier to understand than kilohertz, but that doesn't really matter. So in this case, you have 500 kilohertz of refresh rate, or you have 2 microseconds, how long it takes to make all the points, all the 9 points here. And this now leads to the first important number. It's the dwell time per click. You remember the dwell time is how long one diffraction pattern is active. Let's say it this way. So you have the point, you have one of these 9 points, and you click here, and then this is the time how long the diffraction pattern which is generated by this point is seen here. And this dwell time per click, which is let's say a generic number only, this is the refresh time divided by the number of points. So we have this refresh time here, and we have the number of points which are given here. And in our example now, one of these diffraction patterns, which is generated one after the other, just lives 222 nanoseconds. This is, I think, quite short. So you have 1 point here, you have the diffraction pattern 220 times nanosecond later, you switch to the next point, you have the next diffraction pattern again, it lives 222 nanoseconds and so on. So this is an important number. And in this case here, the dwell time at each position is the same, because I have 1 click per position. So in this case, the dwell time is also 222 nanoseconds. So if you want, so this is a generic time, and this is the time which really applies to your pattern. So by defining this, you define how long such a point or how long the diffraction pattern generated at this position lives. And again, you can click more than once. It's the same example. I have clicked twice here in the center, which means that I have now, oh, the points is missing, my mistake. So this, again, number of clicks here is 2, which means that the number of points is increased from 9 to 10. You still have your 9 points here, but you now have in the center 10 points, and the effect is a little bit funny. So this is, of course, the same. The shape refresh rate did not change. And now what we have is the dwell time per click is now only 200 nanoseconds, because you have your 2 microseconds divided by 10, which is 200 nanoseconds. So the time per click is reduced. But here in the center, you have 2 clicks. Following this formula, you have to multiply here by E equals to 5 is 2. So at this point, you got 400 nanoseconds of dwell time now. So the funny effect is, if you increase, let me just shortly go back. If you increase here 1 click, you will not double this number from 222 nanoseconds to 444. You only will increase it to 400 nanoseconds. If you are close to an effect in your process, this might be of importance. Usually it might not matter, but if you are close to a threshold for whatever, it might be important that you do not double the time, but you do something like doubling the time. What you do is you double the time with respect to the other points. This is correct, but you do not double the time with respect to the shape you had before. And
short question, does that mean that so when I'm staying at one click and for, let's say, 2 clicks, that the shape in between is not refreshed, so the intensity is not changed at all? Or would that rather mean that the pattern is again loaded, or I'm not sure how to put it?
This was one of the questions I also asked. In principle, we should ask Eyal, or Benayahu we should ask, but he's no longer there. So my understanding was the software sets the point again, which means one of the problems is the situation between 2 clicks is, to my knowledge, not completely defined. So just imagine what happens. They have 32 electro-optical controls, and they got some voltage to do something to make this phase shift, and then they get again the next set of voltages. And this happens within these 12 nanoseconds. In the case where we have times which are 200 nanoseconds, I guess it doesn't matter because it's only 10% or even less of the time. If you are close, if here would result in 20 nanoseconds instead of 200, then I guess it might cause some troubles. I think I can remember that Benayo said it's not really clear what happens.
Okay, thank you.
Probably stays on the last state, but maybe if you have discharge or I don't know what, reflection in the cables or whatever, it might do something in between which is not really controlled. And if you are close here with your T click to the minimum click, the duration of 12 nanoseconds, then I guess this might cause problems. That's a very, very good question.
Thank you.
So if you are very fast and have a lot of points, keep this in mind. I mean, this number goes down if you increase the number of points. There are shapes in the Civan generator which have 100 points, I guess, or 50 at least. So if you have high frequencies and a lot number of points, then you end up with very short time durations per click, which might do something unexpected, if I can say it this way. And this is the other side, as I've already started saying. You have this 80 megahertz, so these 12 nanoseconds. And of course, your T for 1 click should be bigger than this time, but I haven't wrote it down. But to my opinion, it makes sense for a lot of reasons, for other reasons maybe also, really to have a defined situation that you say the time for 1 click should be at least 10 times the minimum dwell time. So maybe one should write it even down,
Well, I have a question. All these equations and numbers that's on the plane on the focus position?
The times have, to my opinion, nothing to do with the far field. The diffraction pattern only exists in the focal plane if you have a plane wavefront before, so in the far field. Here I agree. So everything which is intensity or fluence distribution only happens in the position of the far field. So for a plane wave in the focal plane. Everything which is time is given by the electronics, and that's it. That's how fast the system is creating stuff. So these are in here in time. Does this help? Okay. I hope you have been happy with it. Coming back to the shape generated, the next thing you can do is defining sequences. Wrong title here. Defining sequences, you have to define the duration, how long a shape lives now. So this is the third number that they have introduced. They have the number of points, they have the frequency, the refresh frequency for the shape. And now the question is, how many times or how long is such a shape living during the complete process you are doing? It's called shape duration. Maybe persistence would be the better name. So it's called shape duration. And here it's a time. Unfortunately, here it's a frequency, here it's a time. Of course, I have again also defined the other thing, and I called it shape duration frequency, which is physically not very nice, but however, it's then easy to identify. So we have the shape duration, 2 milliseconds in the example here, and the shape duration frequency is 1 over this time, which is 1 divided by 2 milliseconds, so it's 500 hertz. So if you change between two shapes with a duration of 2 milliseconds, with 500 hertz, the two shapes are changing. So this is the third number which plays a role. And here also another implication comes out. This shape is now drawn n times during these 2 milliseconds. So what you have this moving of the beam, the creation of the 9 points here, or 9 diffraction patterns. And the question is now, how many times is this done during the 2 milliseconds? And in this example, we have the time for the shape, which is 2 milliseconds, and we have the refresh rate, which is 500 kilohertz. So this shape is drawn 1,000 times. And this is a similar question to what happens between the points. You can also ask what happens between the shapes. It's more or less the same problem. If you go here to 1,000 times, it doesn't really matter. It's a lot of drawing. If you have the number selected in a way that it's close to 1, then it might run into difficulties that you have no really defined shape at all. So it's important really here to set the things that the number is quite big if you want to have the shape. It depends on what you want to have. But then you must here have a big number. So this is important, and of course it's recommended that this is an integer. Otherwise you end up with half a shape, and if you then make 2.5 shapes or so, that might be a problem. So you should select the two numbers in a way that here you end up with an integer.
Shape duration has its own ID number, or how are you going to call them and organize them? Like if I want to do at the some square shape welding, so I want to go over the corner and I want to change the shape style of looks, the duration time, how that will be changed.
That's again a very interesting question. I guess I cannot completely answer it. To my knowledge, there is collaboration started with some scanner or machine manufacturers and Civan. One thing is in this case, you must synchronize your local beam position on the sample or your beam path. You must synchronize with the shape. And there must be some interaction with the machine to the laser, which I cannot answer. Sorry. What you can do, you can calculate, of course. You can say, I'm now welding for 10 centimeters with 1 meter per second, or with 10 centimeters per second in one direction. So you have 1 second, this shape, and then after 1 second, you change it. Then you have maybe the correct shape then for going around the corner. If you want to be really correct, you must have some synchronization of the laser with the welding, with your geometry of welding or geometry of cutting. And to my knowledge, for this you must contact Civan. I don't know how it's solved and if it's solved. You must ask Ami if their welding head can do it already.
Yeah,
Maybe.
so it's at the moment with the Smart Move laser, through the software, you have the option to, I will have to double check it, but I'm pretty sure define it by location, which beam shape you want to use, and it's sort of
Yeah,
different than the sequence.
You can
But
define it
my
in the
question
pen.
on the software, I mean, on the software, like a duration shape is 2 millisecond. Like, how are you gonna select another shape like on the software?
Ah.
So then each shape has its own ID.
Yeah.
Is that how it's working?
That's simple.
Yes.
That I can answer also. In this shape generator software, you have just the next of these rectangular screen aside, ID, next ID, and if you have two here, then after two it switches to the next, and after the time you define there, you don't need even to define the same duration. So you can make a sequence with 24 shapes very easy in the shape generator. I don't have the rest of this, but this is simple and straightforward. Maybe Ami can show you afterwards how this is done. Or you can play around with shape generator a little bit. And Ami, from my point of view, 5.4 has a mistake there. And something does not work.
Okay.
Okay,
Take it
coming
offline.
back. Sorry, yeah. So I think for synchronization with the welding, this is another step which is not at the basics. I would, if you allow me, I would stay for today. I would like to stay at the basics. So this is the numbers we have been defined, and for your convenience, I don't need to explain. You have all again summarized here in one table on this side. So there is no need that you go through the slides. You can just have a look here of how the numbers are defined. The black numbers are defined by the user. All the normal font values here are then resulting from what you have defined. So if you define a set of things, you end up with a lot of other numbers which are important for the process. So and now maybe this is the last step now for today. So time constants are time constants. One thing is they must fit to the principle of the laser. So you cannot go too fast or too slow or what we have discussed already. So you need to have time constants which are in the range of the electro-optical and mechanical properties of the laser. But what is much more interesting from my point of view is what does these time constants now mean for the laser process? And this was very nice for me. About 2 weeks ago, it was very hot, and I was buying a ventilator. And then I had my grandson with me. Let's move again. And then he's 3. At this time was about 3 years old. He was looking at the ventilator and said, "Hey, what happens? In the beginning, I see the wings, and then they disappear." That I think was funny. And for me, this is one of the things which is really behind what happens with the time constants that are provided by the laser together with the process. And I guess one needs to distinguish and define process regimes. And let me show you just as 2 examples, relax a little bit from what I have taught up to now. This is a nice film out of the internet, out of this paper. You get this as supplementary information. You see synchrotron video of welding. So this is critical instability at the tip, and what you can see is spiking in pore formation here at the tip of the capillary. You can see here the bubbles. It's not yet pores, it's bubbles. You can see how they emerge out of this process, and of course, people want to get rid of it. And if you look at the time scale here, the frame rate was very, very fast in this case. You can see that the formation here, if you look at it, is within about 4 microseconds. So it's very fast in a very short time. If you switch between times and frequencies, this corresponds to about 250 kilohertz. So very fast. if you look at the film I have shown in the beginning, here the frame rate was 1 kilohertz about, and these huge bubbles, which end up here as pores, you can see it already. These huge bubbles, the generation of these bubbles in aluminum, it was in the range of 1 kilohertz, so 1 millisecond, which means if you look at time constants which are provided by the laser and time constants which come from the process, it might have a completely different influence in this case than in this case. And this is, for me, important, or really important, that you relate these numbers. And what I would like is to distinguish between 2 or 4, depends on how you define it, mainly on two different regimes. One is I called dynamic beam shaping. So we have a dynamic beam. You remember, that's what we have seen in the beginning. You have this shape or this point which moves through the melt pool, and the capillary follows really, I can show it again, the capillary can follow the beam which steers around here in the melt pool. So you can really see how the capillary moves around. The process can follow the beam. I have also X-ray images of it. You can see the capillary which is moving around, and you can even see an IC effect here. So I'm showing it. There is a pore generated, or a bubble here, and then with the next pass, the keyhole passes again and degasses the bubble, and you get rid of it. So there is definitely situations where it might be very interesting that you have a moving beam, or a moving point in our case, which moves through the melt pool in this case here, and the process can follow this movement. The second situation I would like to call quasi-static dynamic beam shaping. So in this case, the beam moves much faster than the process. This is a film from the FSW. Again, keyhole welding. You remember this graph of the moving point here. We had the welding, the point was moving along the axis, and if you have a closer look, you can see here the values. It's very fast, everything is very fast. And the shape refresh rate was now 100 kilohertz. The shape was only this line here. And what you can see, if you look at it, you can see the beam moving up and down here, the front of the keyhole. But the keyhole itself, apart from the usual fluctuations, does not respond to what's going on with this laser. So if you are very fast and the process reaction is quite slow, then you end up with a response of the process to the beam shape, which is almost static. So we would have the same result probably if the beam would have this shape here. So I would call this quasi-static, and this means that the beam moves much faster than the process or the point. And this is a nice example. Then you can make a triangular beam shape, and remember, the point is always moving here around in this triangle. I don't exactly how the shape did look like, shape did look like. But you see, the movement is so fast that the melt pool itself just adopts the shape of this triangle. So if you move very fast, what you get end up is really with a shape. So this is what I would call, this is a shape. If the beam is so fast that the process cannot follow. And there's a very recent result. Michael Savagna, Jonas is also here today. They have made a nice experiment. These two shapes, it will be presented at Lane in next week or so, or 2 weeks later. The two shapes, one is the high, just a single point, which is high in the center, and then the 4 points here. And what you can see is when the single point, you have this deep weld. This is a cross-section, longitudinal cross-section. If you have the 4 points, you have this weld here. So what you can switch is between a deep and narrow weld and a weld here, a wide weld, but not so deep. So the cross-section would be the same approximately, I guess. So this was with 10 hertz. You see here was the square, then the single point, the square, single point, and so on. And if you now increase the frequency of this is now the frequency between two shapes, so the shape duration. So this is the shape duration frequency. So 100 hertz is 110 milliseconds. So the duration was 10 milliseconds in each case. And what you see is that very, very nicely, the spiking here, or it's like a spiking if you want so, the excitation with this narrow spot here at the bottom gives really deep tooth or root of a tooth in the material, so like a spike. Then it goes back. The system has time to go back to the original width, depth of the 4 points. So we have here the 4 points, and then it switches again up to the single point. So with 100 hertz, the system can very, very nicely follow the shape frequency. So switching from this shape to this shape. If it comes to 1 kilohertz, 1000 hertz, you see that there is still, the peaks are about with the correct distance visible, but now the amplitude has changed. So you have still a response of the process which fits more or less to this, in this case now it's 1 millisecond shape duration, to this 1 millisecond, but the process has not enough time to recover to get back really to this shape here. If it wants recovering, but then when it starts going up, then again this small point makes the deep spike here at the bottom. So when the amplitude here starts changing, then you are in the transition regime, and if you are getting much faster, if you go to 10 kilohertz, so 100 microseconds shape duration, then you can see that it's more or less random again. So you have some spiking, something happens, but it's not synchronous to what you are exciting. So this is what you can really expect from your process. One of the important tricks is that you really need to define these times and frequencies that they fit to what you want to achieve in your process. So you have to look, do I want to have a kind of perforation? Then this is the nice thing. If you want to have this type here, sometimes deep, sometimes not, then this is the correct frequency. If you want to end up here with some, let's say, average steps, then you must switch very fast between the shapes. So this can be summarized. I'm approaching the end. You have either a moving point or you have switching shapes. Come on. Now it switches. It's a little bit slow, sorry. So it switched between the shapes. You have dynamic beam shaping if the shape refresh frequencies are shorter or are smaller than the process frequency. Remember, I have defined this typical process or issue frequency or time, and now I relate the numbers we had in the shape generator with the process. So this is dynamic beam shaping. You have the shape refresh rate, which is smaller than the process, or here the same as formulated in time. And in this case, the beam can follow the diffraction pattern. So what you have is this moving beam or wobbling. But this is the case which is also addressed with, let's say, with slow laser systems. If the shape duration frequency, now this is the refresh rate, this is duration frequency. So we are speaking about this side here, is smaller than the process, then what happens is that the process can adapt to the shape in a sequence. And unfortunately, this film has troubles to run fast enough. Let me just go out of the presentation. I can't. So, sorry. And go back to the presentation again. Maybe we can see the films correctly. Now it's getting faster. So looks like So that's what I have shown. And now you can see how it switches from one shape to another. So this was just switching the one triangle in front, once the tip of the triangle in front, once the base of the triangle in front. So this is what happens if the shape duration frequency is smaller than the process frequency. If it comes to quasi-static beam shaping, then the shape refresh rate is much or is higher than the process. Then you end up with a single shape here. So the process can adapt to the shape, then you have to set up this. And if the shape duration frequencies now are bigger than the process, then you are very fast. I call this mixing the shape. You can't see it that nice, but what you can see here is that if it's very fast, then you end up almost is a constant weld pool. This is just calculated, but I guess the reality might be similar. So here you can, whenever it changes, you can see that there is a pressure wave and the weld pool does change. In this case, you end up with a quasi-static weld pool, which has always the same shape. That's why I called it quasi-static. So these are the four situations that I've shown in the beginning, and these four situations can nicely be explained with all the frequencies and process times that are defined in the shape generator. So if you now go to your process and if you want to solve an issue, you can start off thinking, first, what is the cause? Maybe the fluid flow is too fast. Then the question is, how can you alter the speed of your fluid? For example, making the melt pool wider. Then this means that you say, I want to have a narrow capillary. I want to have a wide melt pool. That makes sense then to move the beam. So you go up and say, I want to move the beam, and to move the beam, I must set up the shape refresh frequency smaller than this typical process frequency. And then I end up, if I'm in this situation, I end up with the moving beam. So this is, let's say, the next step. Now to start thinking of, I have these regimes, and the question is now, where do I need to go to really have the correct influence on my process, which I want to solve. And these time constants must be known, no chance. You must know the time processor or the issue processes, times for the issues, in order to be sure that you select the correct method to influence them in the correct way. So this is the very important stuff. And this is the short commercial for today. This is what really is the very, very, very nice thing about the Civan laser. From my opinion, this is the only laser on the world that can do it all. So you can really think of what you want to solve. Then you can think of what might be the methods to solve. And then the laser, if you set everything correctly up, you can really go to the regime which you want to go. This is with standard systems or other, let's say the today's standard systems, not possible. So Civan is really the only laser that can do it, and that's why I like it.
What is the distance between center to center of the point, like physical distance?
Between what and what?
Between center of one point to the center of the other point, like what is the physical distance?
Yeah. Let's go shortly back to this picture here, I guess. You have the possibility to change it, to set it to, you can change to a 64 matrix. So what you can set is the point from here to here. The minimum distance, sorry, I must switch a little bit through the numbers. Where is my table? Here we are.
So the scale on this net here, is it like a micrometer?
So this is
just arbitrary numbers.
Yeah, I will show you. The table is the table I've shown you is the key. So what you have is the maximum in x direction, the Z maximum of the point, depends on the focal length of the lens. If 1 meter is simple, huh? If you take 1 meter focal length, your maximum Z point, the green Z point, is 172 micrometers away from the center. So if we go back to this picture with the single point, so this was 170 micrometers, and this can be here in this case defined in 16 steps. So this is about 10 micrometers from here to here with a 1 meter lens. It depends on the length. So with a 1 meter lens from here to here is about 10 micrometers. You can even use a smaller grid, then you have about 10 times, no, 5 times more. Then end up with 2 micrometers. This is one thing. You can set it in the range of a few micrometers. But of course, if you have this central point here, then you have a diameter which is given by this formula. And this means if you just move here by 1 micrometer, this is 170 from here to here to with the 1 meter lens. Doesn't make sense. It's still the same. So the one thing is the resolution of the face front, how you can start to position it. The other thing is when does the process remark that you have moved the beam at all? And maybe 10% of the diameter makes sense. So in this case, the diameter of the beam is about 100 micrometers. So it's also about 10 micrometers. Was this the question?
Yeah, the center of like this Gaussian, like the big maximum peak, to the second one, which is what is the side lobbies, you call it lobbies. What is the distance from the center to center? Like I want to understand at the end of the day the heat distribution that I'm going to apply to my material.
Yeah.
So I want to understand the distance of each point, like from center to center. How much is it?
So from this point to this point, it's 10% of the diameter of the active area. So from the center of this, can you see it on the with my mouse? From the center of this point to the center of this point is from 0 to 0.1. So this is 10% of the diameter of the active area, and the diameter of the active area is for a 1 meter lens, 1 millimeter.
Perfect.
So it's 100 micrometer.
Thank you.
That's dependency. So you can really go into this graph, then you can look at the numbers here, and this is normalized to the diameter of the active area, and here you find the diameter of the active area for different focal lengths, or if you want so, you can calculate it yourself. So this table is just for the lazier people that you can take me. But you see the dimensions about.
Great, thank you.
You're welcome. So, and as for the conclusion, so this was, if you want, so this was my conclusion here. Let's show it again, because I think it's very, very important. I have made another conclusion slide. So the first part is you have really to consider that it's a diffraction pattern and not a point. Very, very important. That's more or less the summary of the first part. And the summary of the second part is there is a lot of times and frequencies which play a role, where you can define when is a point, when is a sequence of points a moving beam, when it's a static beam, and so on. I have here written down again all these relations. There is no need to repeat it. You will get the slides if you want to have a look at what exactly happens. Then you can look here at these relations. And also, if you find errors here, please tell me. Maybe you can understand now why I had that many discussions, mainly with Jonas, to understand this. And the other thing, what I can suggest you really is, if you are already using the laser and you have processes which work, go to these numbers here or to the slide before and look or try to find out where your process is, I guess you can learn a lot of how you can handle problems. And the last slide for me today is a short outlook. This was now really basics. I'm sorry, it's hard stuff, I know, and you have really carefully reconsidering it to understand, I guess, to 100% what's going on. I'm still not in this stage. The next is, of course, what happens with how can you then deterministically influence your process. Ami has shown in the beginning, you identify a cause, you determine possible solutions, and you relate it then to what the shaping is doing with your process. So this is what I have shown now, how these numbers come, but the first 2 points are, of course, still open. There are a lot of approaches. You can do analytical estimates for moving beams, moving heat sources on the surface, analytical estimates. Of course, you can rely on experience that you have had with different shapes to see how you change the keyholes to make the mixture. And then I guess this is the next step to really find solutions for very constructive beam shaping. And you must stay in contact with Ami, of course, to have it. And this was the question, when is a shape a shape? And nice answer, always, sometimes, never. Depends on what you are doing. So that was it for the moment. I hope some are not asleep yet. And I'm very open for questions also afterwards. If you want to write me or ask me, Ami can give you the contact data. Thank you very much.